Can you see anything? Screen capture. I was afraid it wasn't working there for a minute. Good evening, everyone. Welcome to my YouTube live event entitled Twinkle, Twinkle, Little Star. For those who don't know me, let me take a moment and introduce myself. My name is Mark Gillette, and I'm a NASA JPL Solar System Ambassador. I will explain in a couple moments exactly what that means. I'm a native of Central Florida. I live not too far from Orlando. In addition to being a solar system ambassador for NASA, my full-time job is I'm a sociology professor at Valencia College in Orlando. I've been teaching there for 25 years. You might ask yourself, why is a sociology professor talking about astronomy? And the simple answer is, I really enjoy talking about cosmology and astronomy. So over the last few months, because of COVID-19, I've been doing these YouTube live events, and I have a few more that are scheduled, and I will be sharing that with you in just a moment. So I'm going to go ahead and miniaturize myself, put myself down here in the corner, and bring up my PowerPoint slides. I would like to acknowledge a few of the libraries around the country that have promoted tonight's event. We may have some attendees from the Winfield Library in Illinois, and that was promoted by Don. So Don, if you're there, good evening. The S.W. Smith Memorial Library in Pennsylvania. Hi, Mary Grace. The Technology Engagement Center, Rutherford County Library System in Tennessee. Hi, Kathleen. I know you're a big fan and glad to have you. The Solano County Library in California. Hi, Jennifer. The Cudahy Family Library in Wisconsin. Michelle. The Lake Dallas Public Library in Texas. Emily, I've been working with Emily quite a bit setting these up, and she has left the library but said that she will continue to attend the events, and I'm hoping that she's here tonight, and Natalie is taking her place. So hi, Natalie. The Geauga County Public Library in Ohio. Amy. Atagua Prattville Public Library in Alabama. Hi, Rachel. The Moores Memorial Library in Pennsylvania. Trish. Canal Fulton Public Library in Ohio. Jennifer. And last but not least, the Prairie Trails Public Library in Illinois. Niani. So I'd like to welcome all of you, be you family, friends, patrons of these libraries or other libraries, former or current Valencia College students, and anyone who just came across my YouTube channel and wants to attend. And indeed, you would do me a great service if you feel comfortable doing so. There's a chat box, whatever device that you're using, and if you would feel comfortable telling me how you heard about tonight's presentation by putting that in the chat, I would highly appreciate it. Tell me both where you're from and how you heard about this. I would appreciate it. Speaking of the chat box will be available throughout tonight's presentation. If you have any questions, feel free to put those questions in the chat box. I will be pausing periodically throughout tonight's talk and looking over here. This is why I will be looking over here to see if you have any questions that I can answer. I would like to tell you that I will not have answers for all of your questions. I do not have a degree in astronomy or physics. My degrees are in psychology, sociology, and higher ed. But I do quite a bit of study in preparation for these presentations. So hopefully I have an answer for you. If I don't, I will admit I don't have an answer. I just won't make one up. So again, I am a NASA JPL Solar System Ambassador, and this is a volunteer program that's run by JPL for NASA. So I am a volunteer. I do not work for NASA. I do not get paid by NASA to do what I'm doing. I'm doing it simply because I thoroughly enjoy and love what I'm doing. And I want to share that enthusiasm with anyone who's willing to listen to me. So You are my audience, and I appreciate you being here. I will ask if you could please subscribe to my YouTube channel and turn on notifications for my YouTube site. And the reason I ask you to do that is because what I do is periodically place a short little video, an ad, in other words, talking about upcoming YouTube live events that I will be holding. And so let me speak of those right now. I have my fall schedule all put together. So please mark your calendar for these dates if you are interested in talking about the planets, or be talking all about the planets of our solar system, in addition to what's called exoplanets, which are planets outside of our solar system. That's going to be on Wednesday, September 30th, starting at 7:30 p.m. Eastern Time. And please note that all of the times that you see up here are Eastern. And I know that I have some people that are attending that are not in the Eastern time zone, so you will want to adjust that time as you need to. And then you're going to notice that I'm moving my presentation to Sunday evenings. What I've been doing is doing them during the week, and I thought that I'd try in a weekend, specifically a Sunday night at 8 o'clock Eastern Time, to try to make it easier for people on the West Coast to participate in my live events if you so want to. So on Sunday, October the 25th, starting at 8 o'clock p.m. Eastern Time, I'm going to be talking about some of the moons of our solar system. Then on Sunday, November the 22nd at 8 o'clock p.m. Eastern Time, I'm going to be talking about galaxies, and I've entitled that presentation Galaxy Quest. And then to wrap up the year, on Sunday, December 20th at 8 p.m. Eastern Time, I'm going to be talking all about rockets, and I've entitled that one 3, 2, 1, Liftoff. So if one or more of those strike an interest with you, please make sure that you mark your calendar, join me back here on YouTube Live, do exactly the same thing that you've done, come back to my YouTube channel about 5 minutes before the event time listed here, and look for that YouTube Live event. All right, so with that said, here's tonight's agenda. I'm going to start with a definition of a star, and then we're going to talk about two concepts that will come up a couple times throughout tonight's talk: a light year and Kelvin, Kelvin being a measurement of temperature. And then we're going to start with a look at our star, the sun. We will look at the the life cycle of a star. We will talk about what makes up a star. We will then wrap it up with classification of stars and Q&A. So that's our brief agenda. So I'd like to talk about our star, the sun. And indeed, our sun is a star, and in fact, a pretty normal star. How do we define a star? A star is a sphere of gas held together by its own gravity that generates energy by nuclear fusion in its hot central core. All right, so what does that mean? Basically, here's what it means. Out in the universe, there is clouds of dust and gas. And sometimes those clouds of dust and gas start to come together. And as they come together, they start to mix together and to grow. And once they get to a certain point, then they kind of ignite through nuclear fusion. And I'm going to talk a little bit more about this later on. But so that's what a star is. And there are hundreds of billions of known stars in our Milky Way galaxy alone. And we're only talking about our galaxy. There are hundreds and thousands of galaxies out in our universe. And so that means that there could be countless number of stars out in our universe. Here are some general statistics and information about stars, or our stars specifically. It takes light about 8 minutes to get from the sun to the earth. It's about 93 million miles from the Earth to the Sun. And because light travels at a definite speed, we'll see in a moment 186,000 miles in 1 second, it takes about 8 minutes for the light from the Sun to get here to Earth. So that means, in essence, that if the Sun decided to just shut off and no longer give any light out, it won't, don't worry about it. We wouldn't know it for 8 minutes. Okay? The Sun makes up 99% of all of the mass in our solar system. In other words, the Sun is really, really big. The Sun is roughly about 4.6 billion years old. It's a middle-aged star. It was born in what we call an open star cluster. And what's an open star cluster? It's basically a loosely bound group of new stars that are all born at the same time together. It has a hydrogen burning lifetime of 10 billion years. Now, I mentioned a moment ago that our Sun is about 4.6 billion years old. So by doing some quick math, you can deduce that our Sun is roughly halfway through its life. It's middle-aged. The Sun converts 600 million tons of hydrogen into helium every second via nuclear fusion. All right. So I've already mentioned a light year. What is a light year? A light year is a measure of distance, not time. It's the distance that light travels in 1 year. And so, as I mentioned earlier, light travels specifically at 186,282 miles per second. So light travels really, really fast. So in a year, light travels roughly 5.8 trillion miles. We know nothing that travels faster than light. I have a short little video that I'd like to show you about what a light year is. Okay, so back to my presentation here. All right, so that's a light year. I also want to mention temperature conversions, because this will become important when we talk about classifying stars. So we in the US are very familiar with the Fahrenheit scale system, which is over on the far left-hand side of your screen. We all know that water freezes at 32 degrees Fahrenheit. We all know that water boils at 212 degrees Fahrenheit. But scientists don't use Fahrenheit and they don't use Celsius, which is the temperature measurement that's used in most of the world except for the US and a couple other countries. Scientists use the Kelvin scale. And you can see that absolute zero on the Kelvin scale is equivalent to about minus 459 degrees Fahrenheit, which is very, very cold. Water freezes at 273 degrees Kelvin, and it boils at 373 degrees Kelvin. You don't need to worry about this. There won't be a quiz on this later, but I did want to mention that you're going to see Kelvin in just a few minutes, and so it refers to temperature. All right, so speaking of temperature, the surface temperature of our sun is approximately 10,000 degrees Fahrenheit. I'm going to keep this in Fahrenheit since that's what most of us understand. The interior temperature of the sun is roughly 27 million degrees Fahrenheit. So, of course, it's very, very warm. On the left-hand side of your screen, you can see that the sun goes through cycles. Indeed, the sun has an 11-year cycle that it goes through. And so, let me bring my pointer up here. You can see that sometimes the number of sunspots that it has, and that's what this axis is measuring, are very, very low. But sometimes it has a lot of sunspots. And so if you kind of look at what's happening here, it goes through roughly an 11-year cycle, all right? And so right now, we are in the part of the cycle where there are relatively few sunspots, okay? But we can expect in the next few years that it will start to pick up, and when it starts to pick up, not only does it have more sunspots, it also has the potential to cause more havoc with us here on Earth, for example, with our electronics. But that's another issue for another day. On the right-hand side of your screen, you see a picture that I actually took of the sun with a telescope. Now, for those who may not know, especially those young people that might be watching tonight, you never want to go outside and look directly at the sun. Okay, this can definitely cause blindness, so never ever do that. And indeed, even when I was using my telescope to take a picture of the sun, I couldn't just simply take a picture with my camera and with a normal telescope. I had to use a special filter to filter out some of the damaging light that could damage my camera and my telescope. All right, and so that's why the sun kind of looks the way that it does. But what I'd like you to look at is this little feature right here. That little feature that I'm pointing to is what's called a solar prominence, okay? And that solar prominence extends, this is the surface of the sun, this extends roughly 10 to 12,000 miles from the surface of the sun. Okay, so that little thing right there is 10 to 12,000 miles long. Now I put this little thing in here, and this is a little tiny picture of the Earth. The Earth's diameter is roughly about 8,000 miles. So that means that we could take the Earth and we could put it up right next to this solar prominence, and we'd still have room left over. So do compare the size of the sun, at least what's showing, to our little tiny planet Earth. Quite an amazing difference in size. All right, perhaps one of the most popular satellites that's exploring the sun right now as we watch tonight's presentation is called NASA's Solar Parker Probe. This was launched on August 12th, 2018, using a United Launch Alliance Delta IV heavy rocket from Cape Canaveral, Florida. This satellite will get closer to the sun than any spacecraft before it. It will get as close as 3.83 million miles to the sun. And you might think, 3 million miles, that's a long way. Well, when you get 3 million miles from the sun, that's actually not a long way. Okay, that's pretty close to the sun. And indeed, this is the patch. Every NASA mission has an official patch, and this is the official patch for the Parker Solar Probe. And you can see that they have dubbed their little saying or logo, a mission to touch the sun. They're not actually touching the sun, but they're getting close enough. All right. So this satellite will use 7 Venus flybys, or what's called gravity assist, over 7 years to gradually shrink its orbit closer and closer to the sun. The Solar Parker probe is named after this gentleman right here, Eugene Parker. He is a retired astrophysicist from the University of Chicago. This is the first NASA mission to be named after a living person. Generally, they're named after people that have deceased. He coined the term solar wind, and I'm thinking that probably all of you have heard that term at one point or another. At its very fastest, this spacecraft, and this is an artist's rendition of what it looks like, will travel at about 430,000 miles per hour. The mission is scheduled to end in 5 years, 2025. And this is run out of the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland. I want to show you their website because they have a really cool website that they have put together for the Solar Parker probe. And you can go back and take a look at this on your own time by going to parkersolarprobe.jhuapl.edu. And that basically stands for Johns Hopkins Applied Physics Laboratory.edu. And so right now, the spacecraft is traveling 50,495 miles per hour. And currently, it is roughly about 66.7 million miles from the sun. I also would like to show you something called NASA Eyes. Now, for those who have joined me before, you have heard me talk about NASA Eyes. And this is a really cool program that PL in California, the California Institute of Technology. If you have not heard me talk about it before, I highly recommend that after tonight's talk that you go to Google and type in NASA Eyes. You will download a little software, and there are different things that you can take a look at. You can look at our solar system, you can look at planets, you can look at exoplanets. And so this one is Eyes on the Solar System. And I'm going to scroll in just a little bit, and I'm going to stop, and right here you can see the current position of the Parker Solar Probe in our solar system. I'm going to zoom in a little bit more. And what I'm going to do is I'm going to go down here to the bottom, and I'm going to speed this up. You can see, if you look in this box here, you can see the time and the date will start to speed up. And then you can see things start to move. And so you can see that the Parker Solar Probe will be coming as close to the sun in this particular orbit around September 25th, 26th, 27th until it heads back out to prepare for another orbit. So I'm going to go really fast, and you can see that it's going to come back in again around January. It's going to go back out, and so on and so forth. So this is a really cool program. I highly recommend that you go take a look at NASA Eyes. And not only do you see Parker Solar Probe, you can see all the other planets, other satellites that are out there, and just check out all kinds of cool things related to our solar system. All right, let me go back to my presentation here. See if I can pick up where I left off, right there. All right, so any questions? I'm going to pause for a moment. Sean's saying it's a great website. Yes, it is. Great, it sure is. All right, so Twinkle, Twinkle, Little Star. That's what I entitled tonight's talk. And so I have a question for you, and type it in the chat box. Do stars actually twinkle? So feel free to type in yes or no in the chat box. It's a bit of a trick question, actually. But do stars twinkle? Yes or no? Calvary Lutheran Church. Yes, no, no. So I got one yes, I'm getting more no's. No. All right, well, stars actually don't twinkle. That's somewhat of a misnomer. And so stars seem to twinkle, but that twinkling is due to the light that's coming from the star entering Earth's atmosphere, and the light is being bent when interacting with Earth's atmosphere, which then causes the star to seem like it's twinkling, but it's not. In other words, if we could get up above Earth's atmosphere, we would see that for the most part, most stars are not twinkling. And I say for the most part because there are such things that are called variable stars. And variable stars are stars that exhibit light outputs which vary, getting slightly brighter and dimmer with time. Okay? They are stars that are not stable in the hydrogen to helium nuclear burning process. Therefore, their luminosity varies as pressure and temperature changes. So we can kind of say for the most part that if you go outside and you see stars twinkling, that's actually not the star twinkling. That's the light coming from that star interacting with Earth's atmosphere, bending the light, making it appear as if the star is twinkling. And again, there are exceptions like the variable stars. So how far are the closest stars? So the universe is really, 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 really big. Alpha Centauri, it's a star system. It's the closest stars to us. And notice that I said stars. Alpha Centauri A and B, simply often called AB, is a triple star system. And what does that mean? Well, a multiple star system has two or more stars orbiting their common center. It is believed that over 50% of all stars are multiple star systems. In other words, it is now believed that most of the stars out in the universe are at least what's called binary systems. There's not one star, but there's two or more. And that's pretty cool because when you think about it, you know, in our solar system, we only have one star. We call it the sun. But if astronomers are correct, that would be an oddball because the majority of stars out there have two or more stars in their system. And so the closest stars to our solar system is, again, the Alpha Centauri star system. They are about 4.37 light years from Earth. Putting that in miles, we're looking at about 24 trillion miles from Earth. 24 trillion miles from Earth. And keep in mind, these are the closest stars. Okay? On the right-hand side, you see a picture of Sirius. I took a picture of Sirius. Sirius is the brightest star in our night sky. If you look at this, you would think that there's only one star there. Okay? It looks like one single star. But in fact, Sirius is a binary star system, Sirius A and Sirius B. Okay? And Sirius is about 8.58 light years from Earth. So doing some quick math, basically doubling what we see up here, Sirius is roughly about 50 trillion miles from Earth. And that's pretty close in astronomical terms. Okay? So even though they seem far, far away, in astronomical terms, both the Alpha Centauri star system and Sirius are relatively close. All right, let's turn our attention now to looking at the stellar life cycle of stars, because stars have life cycles just like anything that is living. And we're going to come back to this slide a little bit later in the presentation, but here's what I'd like to show you right now. All right, so there are 5 stages in a star's life cycle. Over on the left-hand side, we have the birth stage. Over here, then, we have the main sequence stage. This is like middle age. Over here, we have old age. Here we have death. And earlier, who was it that brought this up? I can't find it. Someone brought up supernovas. I'm going to be talking about supernovas a little bit later. Here it is. And then we have, well, what happens after the death of a star? Okay, so 5 different stages. Over on the left-hand side, we have a cloud of dust and gas, like I was talking about earlier, which when they start to come together and they form what's called protostars. Okay, and then protostars are continuing to gather the dust and gas that's available to them and continue to grow. Stars can grow kind of into 3 different levels: super large stars, average sized stars, including our star, the sun, and very small stars. Okay? Then they're going to live out their lives. Their lives can be a few 100 million years, all the way up to hundreds of billions of years. As a little side note, I'll mention this later, the super big large stars don't live very long. Medium-sized stars and small stars live a long time. When it's time for that star to die because it has exhausted all of its capability to do nuclear fusion, it can turn into a supernova. It can turn into a planetary nebula. That's what's going to happen to our star in about 5 billion years. And then it progresses from there. So again, we're going to come back and look at some of this in more detail later. Right now, I'd like to show you a short little video about the life cycle of a star. Now this video is a little long. It's 6 minutes, but I think it's worth watching. So do enjoy.
Did you know that when you look up in the dark night sky, you are in a way looking back in time? It's really true. Much of the light you see coming from the stars has been traveling across space for millions of years by the time it reaches us here on Earth. Some of those stars that you can see tonight in the night sky may have burned out millions of years ago. If you have ever wondered where stars come from, how they change, and what happens to them when their life comes to an end, hang with me for a few minutes as this episode of NASA Launchpad takes a closer look at the life cycle of stars. And, bonus, we're going to talk a little bit about how each of us is actually made from dead stars. Yeah, really. Most things in the universe have a life cycle. Thankfully, for some things, like these guys, the life cycle is incredibly short. But for other things, like stars, the life cycle can be billions of years long. The life cycles for stars begin in giant stellar nurseries called nebula. If you look at one of these star-forming nebula, you will see beautiful giant clouds of dust and gas. How a star forms is a little technical, so let's hear an explanation from an expert.
A star is basically a nuclear furnace. It's this collection of mostly hydrogen gas, And at the center is really, really hot and dense, where you can actually get nuclear fusion occurring, and that's how you get the heat and the light from the star. In space, you have this collection of sort of diffuse gas and dust particles. It's just sort of everywhere in space. Occasionally, it comes together through gravity. It's attracted to itself, basically. And so you get these giant molecular clouds, they're called, these big nebulae. As that stuff comes together through its own gravity, you eventually get these places where you have enough material where you can start to form a star, where it all comes together and the gravity pushes on it so hard that it heats up in the center, and that heating up is what will eventually lead to fusion and the birth of a star. Two of the most important properties of a star are its color and its brightness. And so if you take stars and you sort of sort them by color, you get anything from red to blue, where the red stars will be the cooler stars and the blue stars will be the hotter stars. So that's really a measure of temperature. And then you can also sort them by their brightness. And so you have the very bright stars, which are usually the more massive stars, and the dimmer stars, which are usually less massive. And just by these two parameters, you can actually tell a lot from a star. You can tell how massive it is, you can tell how big it is, its radius, you can tell how old it is, you can know what stage of evolution it's in, and you can learn about the environment of the star that the star was born in.
As you know, our sun is a star. It is actually a fairly modest-sized star. It is believed that our sun is about halfway through its 10 billion year life cycle. Yes, that makes our sun about 5 billion years old. But don't worry, we're all good for at least another 5 billion more years. So, how will our sun's life cycle play out?
So our sun is a low-mass star, and it's actually going to go through a really long evolution. It's going to be in the phase that it's currently in, where it's just fusing hydrogen into helium for about 10 billion years. And then once it runs out of fuel in its center, it's going to evolve into a red giant star, a red meaning that it's going to be cooler, and it's going to be so large that its outer radius is actually going to reach the Earth's orbit. It's going to be a huge star. And then eventually it'll blow off its outer layers and become a white dwarf star, and that will be its final phase.
So at the end of a massive star's life, we have what's called a core collapse supernova. So the core region collapses in on itself, and the outer region infalls and then rebounds, and you get left with a neutron star or a black hole.
You may have noticed that no matter the size of the star, at the end of its life cycle, most of its material is expelled back into clouds of dust and gas in the galaxy. The life cycle of a star can begin again.
Throughout a star's life, it's throwing off material, and this material has been enriched by nuclear fusion reactions. So originally, really only hydrogen and a little bit of helium was produced in the Big Bang. And all of the elements that we get after that have been produced in either a star's life or in its explosion, if it's massive enough to explode. And that material gets mixed in with the other gases and dust in the interstellar medium and produces the next generation of stars. So every generation of stars that you produce is more and more enriched with material from the life and death of stars.
So what does all of this mean for us? And what is our connection to the cosmos?
All of that fusion that's going on in the centers of stars is creating heavier and heavier elements, and that's how you get basically everything you see around you, from the carbon to the iron, the oxygen, everything. You can't get any of those elements without having a star forming it in the first place. And so everything that your body is made up, everything that you see around you, all came from the center of a star.
Pretty amazing, isn't it? When you look at that periodic table hanging in your science class, it represents all of the natural and man-made elements. Most of those natural elements were formed and fused inside of long dead stars. Yeah, that's right. Everything around you, including you and me, was formed from the remnants of exploded stars and the birth of the universe. We may look and act differently from each other, but we are all made up of the same stuff. Want to find out more? You can learn more about stars and their life cycles from these NASA websites. That's it for now. See you next time on NASA Launchpad.
Isn't that pretty cool? It's pretty cool to know that Carl Sagan, who was a very well-known scientist back in the day, for those of you who are younger, mentioned that we are all made of star stuff, and basically we are. Everything that we know, here is a periodic table of elements, comes from stars in one way or another. And so I don't want to go too much into chemistry. This isn't much of a chemistry lesson per se, but I do want to mention that most of the universe is made up of hydrogen, about 74%, 25% helium, and 1% everything else. And for stars, what it does is it takes all of that hydrogen, it burns it, and makes it into helium. When stars get really, really hot, then it can start to make some of what astronomers call the heavier elements, including everything up to what you see here on the periodic table to iron. Okay? Now, Kendamom asked earlier about supernovas. And so when a super large, a super giant red star goes supernova and it explodes, that explosion, which can occur in less than 1 second, will create most of all the other elements that are here on the periodic table of elements. So look around wherever you are, and everything that you're looking at, including yourself, is star stuff. And indeed, this is exactly what this periodic of elements table looks at. Again, where did the helium and where did the hydrogen come from? That came from the Big Bang that occurred about 13.9 billion years ago. But most of what you're looking at here comes from the death of stars. Okay, pretty cool stuff. How were the elements made? Quick little video on how the elements are made.
You've almost certainly seen a periodic table of the elements, but have you ever wondered where those elements came from? To understand their origin, first we have to look at what defines an element. An atom is made up of positively charged protons and neutral neutrons in a nucleus, surrounded by negatively charged electrons. The number of protons in the nucleus defines an element, but a single element may have atoms with a varying number of neutrons. These are called isotopes, and though these are all still the same element, they vary in their stability. Some nuclei are stable and require large amounts of energy or bombardment by other particles to transform into different elements or isotopes. Other nuclei are inherently unstable and will spontaneously decay. We begin our story with the Big Bang. As the universe expanded and cooled, the sea of fundamental particles began to coalesce, forming the first protons. And a proton is the nucleus of the first element on the periodic table, hydrogen. In the first few minutes, a few more nuclear reactions occurred to create some helium and very tiny amounts of lithium. At this point, synthesis of larger elements was put on hold, until the inhomogeneity of the universe led to the formation of stars, which could become hot enough to allow for further reactions. Many stars start off small, and are fueled by their ability to fuse hydrogen into helium, much like our own sun. Once their hydrogen fuel has been used up, stars which are massive enough go on to fuse together larger elements, while they themselves increase in size and temperature. But there is a limit to a star's ability to fuse smaller elements into larger ones. When small nuclei are fused together, the nuclear reaction releases energy, supplying the pressure needed to keep a large star from collapsing onto itself. But we reach a problem when a star forms iron-56. The nucleus of this isotope of iron is the most stable nucleus in nature, meaning that it can't be fused further to fuel a star. In other words, stellar nucleosynthesis halts at iron. At this point, the star has no energy to overcome gravity, causing it to implode and then rebound to explode in what we call a supernova. During a supernova, intense amounts of heat and gamma rays are produced. These gamma rays go on to break apart some iron nuclei into, among other things, copious amounts of neutrons. Intact iron then acts as a seed, capturing these neutrons and then decaying into new, heavier elements. Some of these new elements can even undergo nuclear fission to produce other ones. This process in a supernova is the primary one responsible for creating every element past iron, all the way up to plutonium. And since it is an explosion, all of these atoms are sent flying throughout the universe. But that still leaves a few more elements. Backtracking a bit, lithium, beryllium, and boron are not made in large quantities in stars. That's because these elements tend to be used up almost as soon as they are synthesized. Instead, they're made primarily by cosmic ray spallation, a process where high-energy particles collide with carbon, nitrogen, and oxygen, removing nucleons to yield these three smaller elements. And finally, every element larger than plutonium was made synthetically by scientists, though plutonium itself and a few smaller ones can also be man-made. In the end, all of these processes are responsible for creating every atom in the universe, including the ones that make up you and me and the entire Earth we live on. Now, understanding stellar life cycles and nuclear processes can be very complex.
All right. So, pretty interesting stuff, I believe. We are, in fact, star stuff. All right. The last major thing I'd like to talk about in tonight's presentation is what's called the Hertzsprung-Russell, or HR diagram. And I've got two of them on the screen. They're exactly the same thing. I couldn't decide which one to use, so I decided to use both of them. I like this one because it actually had stars with different sizes on them, which I think is important because it really shows us in a visual effect that these are big stars at the top and little ones at the bottom. This one didn't do this. However, this one shows color better because on the right-hand side you can see red, and as we move towards the left-hand side, we're going to move to blue. And the red stars are cooler than the blue stars. This one didn't show that. So I hope I don't confuse you. But this one here, let me turn to my pointer here. This is exactly this, just kind of showing it in a different way. So this HR diagram is named for a Danish and American astronomer that shows the relationship between the star's absolute magnitude on this axis here versus their stellar temperature. And temperature is up here on this one and down here at the bottom. Okay? So the absolute magnitude is defined as and refers to the apparent magnitude that a star would have if we were 10 parsecs from the Earth. In other words, what it's trying to do is, because we are so close to our sun, it's hard for us to really put this into perspective. So the absolute magnitude allows us to move far away from our sun and compare our sun to other stars that are out there. Again, keeping in mind that our sun is simply just a star. All right, and so, as I mentioned, the absolute magnitude refers to the apparent magnitude that a star would have if it were 10 parsecs from the Earth. Well, what is a parsec? It's a unit of distance equal to 3.26 light years. All right, so let's take a look at what we're looking at here. On the right-hand side of the HR diagram, we have stars that are relatively cool. Yes, they are 4,000 Kelvin, as I mentioned earlier, so that's still very, very hot. But compared to the stars that fit on this side of the diagram, 4,000 is not too bad compared to 30,000 Kelvin. So the way that you read the temperature on this graph is cooler ones on the right, warmer ones on the left. Okay, and that goes again for both of them. All right. And on this one, we see the spectral class. You can see it down here at the bottom on this one. And stars are divided into 7 spectral classes: O, B, A, F, G. Notice that our star, the Sun, is a G-class star, K and M. Okay, so those are the different spectral classes. And the way that you can remember this, there's a little saying that you can remember this by. O, B, a fine guy or gal, kiss me. That's the way that astronomers remember the different classes, spectral classes of stars. Okay? All right. And so this is a great diagram because what it's doing is it's classifying where the different size of stars are located. You have the supergiants up here, the giants here, what's called the main sequence right here. Okay, notice that the sun is a main sequence star, and down in the bottom left-hand corner we have what's called white dwarfs. Relatively small, but most of them are blue and hot stars. All right. Let's get some general information about stars from the HR diagram. Stars range in mass from the smallest, here are the smallest stars down here, which are only about 8% of the mass of our star, the sun, up to the supergiants, which are 150 times the size or mass of our sun. Okay? The more massive a star, as I mentioned earlier, the real big ones, their lives tend to be much shorter than the small ones. Why? Because they are burning through that hydrogen mentioned earlier much, much quicker than the small stars are. Okay? So large stars generally will last a few million years, whereas small stars can last hundreds of billions of years. All right? We can determine the surface temperature of a star based on its color. As I mentioned earlier, blue stars are hotter, red stars are cooler. Main sequence stars, the ones that are right there in the middle, such as the sun, are in a relatively stable hydrogen burning phase of their lives. All right, so everything's kind of in balance. The gravity and the pressure and the burning of the hydrogen into helium, and so that's why they're called main sequence. They're in balance. Okay, about 91% of stars that are surrounding our solar system are main sequence stars. Okay, of those, 70% of those stars are red dwarfs. Okay, red dwarfs. They're relatively small and they're relatively cool. All right. Going back to this slide, as I promised earlier, how does a star get born? There are clouds of dust and gas that come together. They form protostars. The clouds of dust and gas kind of come together. They start to coalesce. Once they get big enough, they reach about 10,000 degrees Kelvin. Then they start nuclear fusion. And again, what's nuclear fusion? Taking what mostly they're made out of, hydrogen, and converting it into helium. 3 levels of stars: super large ones, medium-sized ones, and small ones. Okay? Let's take a look at the death of a star then. What happens as it approaches its death? Let's take a look at our star, the sun. In about 5 billion years, our sun will become what's called a red giant. It will grow in size, very, very large. It will become so large, it will come to where the Earth orbits the sun and will basically destroy it. We don't need to worry about it. We won't be here. And then what will happen with our star is that eventually it will start to blow off the gases that have accumulated around the red giant, and it will become what's called a planetary nebula. Now, that's a misnomer, and it's a misnomer because many, many years ago, when astronomers didn't have proper telescopes to really determine what was going on, they looked up and they thought what they were looking at was related to planets, when indeed it was stars that were going through their death process. Once this gas dissipates, our star will become a white dwarf. Okay? If we were to go and take a look at the big supergiant planets, Kenya Kenda Mom was asking me about supernovas. Well, eventually they get so big that they end up exploding. And when they explode, that explosion is called a supernova. And it's important that supernovas occur because as we were looking at the periodic table of elements, if we did not have stars exploding into supernovas, we wouldn't be here. Okay? That's how heavy elements are made through that supernova explosion process. So we have the death of stars to thank for us being alive here on planet Earth. And then they can either dwarf into black holes or neutron stars, which will go to X-ray emissions and pulsars. Unfortunately, we don't have time to go into that because we are just about at 8:30 Eastern Time. And so I would like to leave just a couple minutes for any questions and comments that you might have. So Sean, so bigger stars tend to be cooler. Generally, that is correct. Large stars, and I'm going to go back to, if I can get this to go back, to the HR diagram. Your supergiants, a lot of them will be over on this side of the HR diagram. That doesn't mean that you can't have supergiants over here. That will be very warm, okay? So it kind of depends, all right? It does kind of depend. All right, so if you have any questions, please feel free to type them in the chat box at this time so that I can try to answer them. As we are wrapping up, I do want to remind you of my fall series of YouTube live events that are coming up. The planets on September 30th, the moons of our solar system October 25th, Galaxy Quest, all about galaxies, on November 22nd, and all about rockets on September 20th. 3, 2, 1, liftoff. So questions. Does anyone have any questions for me? Don't forget to subscribe and turn on notifications so that you know when I post these little short videos advertising upcoming YouTube live events if you are available and interested in attending. Does anyone have any questions for me about stars? Has our star stayed the same temperature throughout its life? No, it has not stayed the same temperature, and nor will it stay the same temperature. As our star gets older and starts to approach the end of its life, about 5 billion years from now, it's going to become a red giant and it will cool down. Okay? So the temperature of the sun does change. Now, because it is currently a main sequence star, it's not changing its temperature a lot. It's going to change, but not change significantly. But it certainly has changed its temperature from when it originally started and formed as a star 5 billion years ago. Does our sun change size based on its orbit? Does our sun change size based on its orbit? If I'm understanding your question correctly, does the orbit of the sun affect its size? Well, the planets are orbiting the sun. Now we have to keep in mind that our solar system is in our galaxy, and our entire galaxy is moving. It takes about, I believe it's 120 million years for our galaxy to do a full cycle or orbit. And so the sun in our solar system is a part of that. And so the sun is shifting along with everything. But time of the year, does our sun change size based on its orbit? Time of the year? No. If you're talking Edgar 2012, if you're talking about short period of time, like, 2020, 2021, 2022, 23, is the sun changing its size significantly? No. It does change its size, but it's not going to be a significant change in size. I hope that answered your question. What is one of your favorite facts about stars that you haven't mentioned yet? Natalie Drotter. What is one of my favorite things about stars? Well, I've already mentioned that most stars are multiple stars, not just one single star. And so I guess maybe the one thing I haven't mentioned is that it takes a star for the possibility of life to exist on planets that may orbit those stars. And so without the stars, it will be very difficult for life to exist, though it isn't necessary. There are such things as rogue planets. And rogue planets, I'll be talking about this in my planet YouTube Live next month, are planets that are not orbiting a star, their parent star. And so there still is a possibility that there could be life on those rogue planets. However, for the most part, we will need to have a star for life to exist on the exoplanets that are orbiting other stars in the universe. So the possibility that it's providing some type of manner in which life can live somewhere else in the universe. I believe the Earth and Moon does. I'm not sure what that means. How often can a supernova be seen from Earth? Unfortunately, Sean, a supernova cannot be seen often for a few reasons. Number one, we don't know where to look. If we knew exactly where to look, we'd be more likely to see them, especially the small ones. But when we don't know where to look, they may happen and we never know that they happened. If it's a really, really, really big supernova, we're going to see it. There was one that occurred back in the year 1054, and it was so bright that they could see it during the day. You could see it like a star in the sky during the day, and at nighttime it produced as much light as the moon can reflect when it's like a full moon. So unfortunately, we don't get to see them very often. Now, if you keep up with the news, astronomy news, the star Betelgeuse, which is a super red giant, it's been dimming over the last several months, and then it kind of brightened up again, and there are reports that it's dimming again. And so astronomers are starting to wonder if possibly the star Betelgeuse may be getting ready to go supernova. And so that would be really, really cool to be able to see that. Because it's such a big star, we would definitely be able to see that with our naked eye. We wouldn't even need a telescope. Now, keep in mind that if Betelgeuse goes supernova, Betelgeuse, I can't recall off the top of my head, but it's, I don't know how many thousands of light years away from us. So if it blows up, it's not blowing up as we see it. It actually blew up a long time ago because of that light year stuff that we talked about earlier. It takes a long time for light to travel to the Earth. So that's kind of cool. If we see it blow up, it's not happening now. It happened a long time ago. When was the last one visible? And again, I think the last big one was in 1054, but there was actually a supernova in 1987. I think they call it supernova 1987A. It occurred in one of the dwarf galaxies of our Milky Way galaxy. Astronomers were able to catch it with their telescopes, and if you go online after our presentation and look up supernova 1987A, I think that was the last, at least the last big one that was caught, Sean. All right. I heard that there might be some sort of debris, such as gas clouds, blocking the light from Betelgeuse. yes, that could be the case, and clouds can block the sun coming, the light coming from a star, and so it may look like it's a variable star or changing luminosity, but it's really only a cloud of dust. So I guess time will tell the story. All right, so it's 8:36, so we are 6 minutes past the bottom of the hour. But I really appreciate you coming and spending time with me tonight, and I hope to see you back very soon. So please make a note on your calendar about those upcoming events, and if you're interested, I'd love to see you back here. So thank you so much for coming tonight and joining me, and have a great rest of your evening. Bye-bye.